Okay, we're now going to look at some practice problems. So here we consider the system given by this state model with this initial condition. Here's my output. We're going to apply a step input as the input, and we're going to simulate this system, and we desire to see the observer poles and to have them be at -10, -11, and -12. Now we can use this MATLAB script to do the simulation. So here's the ABC matrices, here's the initial condition. I can define the state space LTI object, and notice the D matrix I do as 0 times C times B. So this is one way of getting a zero matrix of the proper dimensions for D. A time vector. Here's the unit step input is just all ones. And so I can use the LSIM command. The LSIM command takes an LTI object, an input signal, a time vector, and an initial condition, if you have one. If you don't have one, it will assume 0 initial conditions. And then it'll give you the output Y. It'll return the T vector. If you do not give it initial condition or a time vector, it will generate a time vector. So that's what the T is. And then it'll also return all the states. So this then will simulate the system. We now want to obtain an observer, full order observer. So here are the poles. And the place command can be used to find the observer gain. So remember, the place command wants to place the eigenvalues of A plus BK. But here we have A minus LC. So BK, K is the unknown, appears on the right, where LC, L appears on the left. So if we want the unknown to be on the unknown L to be on the right, if we take the transpose, so remember the eigenvalues of a matrix are the same as the eigenvalues of the transpose. So if we place the eigenvalues of the transpose of the matrix, then we have A transpose minus C transpose L transpose. So then the unknown L is on the right. And then when we're all done, we transpose again and we get the matrix of proper dimensions. Our observer has this as the A matrix, A minus L times C. This is the new input matrix. This includes the input Y and the input U. I have chosen as the output to be the C matrix to be just the identity matrix. This will give us all of the observer estimate values. And then here is the D matrix for this observer, just 0 of proper dimensions. X hat, then we can simulate. So notice we've already simulated and obtained X. To obtain the simulation of the observer, we would have this system. And so we put the observer, we look at, so the input to the system now is not U, it is Y and U, Y we obtain from the previous simulation, and also the T vector. And notice I'm assuming 0 initial conditions on my observer, and so this is the simulation I will use. So we've defined the system, we've got the observer simulation here, and when we simulate it and we plot the responses, this is what we get. And you've seen this plot before. So the state of the system, all the state variables start off at 1. Remember, it was 1, 1, 1. And then they go through and do their thing when you apply a step input. The observer states all start at 0. And so you can see there's a transient response in which it takes a while for the observer to converge, the observer states to converge to the system states. And it takes about ½ a second in this case because of where those poles are located. It takes about ½ a second. And as you can see, there's some transient response associated with this. This transient response is often referred to as peaking. And it's caused by the mismatch between the initial conditions of the original system states and the observer states. Here is a system that we're given now. And so this is in discrete time. And so we're going to use, we're going to choose this particular L. This particular L is chosen so that A minus LC squared is 0. That is, it's a nilpotent matrix. So this is a deadbeat observer. We've chosen the observer gain to put all the eigenvalues of the closed-loop system at 0. So even though the matrix itself is not 0, it is nilpotent. If you multiply this matrix by itself, you'll get 0. And so when we simulate that, this is what we get. And so in this case, we're actually going to simulate it with an input that I think it's a sinusoid. And anyway, so you can see again there's some transient response associated with the system and the states, but notice that after 2 steps, the estimate locks on exactly to the state of the estimate locks onto the state. So we have 2 state variables, and so you can see they lock onto the 2 state variables. So that's one of the things that the deadbeat observer does, is it will lock on in a minimum number of steps to the exact value. So in continuous time, it exponentially converges, but in discrete time, we can actually get them to be exactly on. All right, now we're given a system. We're asked to obtain a deadbeat observer. So we have this system, and we can go through and show that in fact this system is not observable. Therefore, we cannot place all the eigenvalues anywhere we want. However, one of the eigenvalues is already at 0. In fact, when we form A minus LC, we can see that one of the eigenvalues, this is actually a triangular matrix, so one of the eigenvalues is already at 0, and the other we can place at 0 by choosing L2 equals to 1. In this particular case, if we choose L1 also equal to 1, that is, this, if we choose L to be this, the matrix, here it says A, should say A minus LC, actually ends up being equal to 0. So we have that situation. So we can still get an observer, even a deadbeat observer, even though our system is not observable in this case. Now for the given system, we're asked to obtain a reduced order observer. So this was a full order observer would use the A minus LC matrix, but now we're asked to do a reduced order observer. And so in this case, since it's 2 states, a reduced order observer is going to have fewer than 2 states, so 1 state. So in this case, the A matrix for the observer is F, and in this case, in order for it to have eigenvalues at the origin, we choose F equals 0, and T then we define to be this quantity, and when we multiply all this out, we get this expression, and we need this all to be 0. This one's already 0. To make this 0, I have an infinite number of choices. L can be given as the sum of T1 and T2, so if I'd let T1 and T2 be 1, then L is equal to 2, and we have a deadbeat observer. Deadbeat observer, reduced order observer. So these are some calculations for observers. Thanks for watching.